Sometimes when we write Lewis structures for molecules like SO2, we end up with more than one structure. And that's what happened when you're drawing that in your lab. So let's look at this. So SO2, we'll put the sulfur in the middle and the oxygens on each side because that'll make it symmetrical. And then each of these has 6 valence electrons, right? So 3 times 6, so we've got 18 valence electrons. And when we put these around, we have to put 2 between. That's 2, 4, 6, 8, 10, 12, 14, 16, 18. That's not going to work, right? The sulfur only has 6, and so we need to make a double bond. So we'll take one of those pairs off an oxygen and stick it in the middle with the sulfur. But really, how is that different than this one? Why did the one oxygen get the double bond and not the other? It doesn't really matter. So those are equivalent. The sulfur is bonded to 2 oxygen atoms, and with our Lewis structures, one gets a double bond and the other doesn't. So the 2 structures are equally correct as Lewis structures. But neither of them really represents the way the molecule is in nature. The molecule actually exists as an average or an intermediate between those 2 structures. So if we look at SO2 and analyze it, we find that actually the bond between the sulfur and the oxygen is more like a 1.5 bond, which Lewis structure can't handle. So what we do, these are called resonance structures, because in Lewis structure we think of it resonating between those 2. So the bonds are in the actual SO2 molecule, the bond between the sulfur and one oxygen, the bond between the sulfur and the other oxygen are actually the same. There's not one that's a double bond and one that's a single bond. So it's intermediate between. The bonds are equivalent. We represent this in Lewis theory by drawing both of these structures and putting a double-headed arrow in between them. This is to signify that the actual molecule is between this structure and that structure. So the real one is intermediate between. On this lab, it doesn't mention resonance structures. It doesn't tell you that you need to write all the resonance structures. And so I would accept either of those as a correct structure. So there's the answer for number 2, right? SO2, there's the structure right there. Let's do another one. Let's do nitrite ion, NO2 minus, and this time the instructions say include resonance structures. So NO2, we're going to put an N in the middle and O's on the sides. And then we have to figure out, well, how many valence electrons do we have? Well, we've got 2 oxygens. They each have 6. And nitrogen has 5. It has a -1 charge, and so we add 1 electron. So 2 times 6 is 12, and 6 is 18. So 2, 4, 6, 8, 10, 12, 14, 16. There's going to be a problem, right? This is the same arrangement with different letters, right? It's just a nitrogen instead of sulfur. Same number of electrons, 3 atoms, and so it's going to end up with the electrons arranged in the same way. The difference, of course, is that this is an anion, and so we need to show the charge. So that's one possible structure. But we could also put the double bond on the other oxygen. So we've got oxygen, nitrogen, oxygen. And this time I'm going to put the double bond over here and the single bond over there. Those are, that's kind of a big negative sign. Those are equivalent structures. We call them resonance structures because the actual structure of nitrite ion is between them. So in 3 and 4 of that pre-lab exercise, do those molecules have resonance? They do. Because you end up with one double bond and you've got different oxygens that you could put it with. How many resonance structures are there for nitrate ion, NO3 minus? There's 3 of them. Because it could be, we could have the double bond with any of those 3 oxygens.
So what does include resonance?